All right, welcome back to our video review series, episode 2 of Unit 2. We're talking inequivalent equations today, and I know that sounds like an absolute oxymoron. I promise it's going to make sense here in a moment. But first, we have to explain what an equivalent equation is, right? If we're going to understand what an inequivalent equation is versus an equivalent equation, then we're going to have to draw some lines, and literally drawing some lines in this case. So an equivalent equation is something that when you put it on a graph, the two lines line up perfectly, or the two parabolae line up perfectly. There is no discrepancy between what one function is versus what another function is. It's just a matter of simplifying the function. And so an inequivalent equation does the same thing, except that the parabolae or the line don't exactly line up perfectly. We're going to see this in a couple of instances, and what we're going to identify here is that those inequivalent equations will still have the same solution as each other. It's just not going to be exactly equivalent. And those inequivalent equations are important because what happens with those is it actually enables you to take a look at a situation and go, okay, I don't know what the answer to this exact equation is, but if I change it around, right, then this other equation that isn't exactly alike still has the same solutions. And so what we're going to do is we're going to turn one equation into another, but they're going to have the same solution. So let's go ahead and get into it. We're going to start off, though, with an equivalent equation. I'm going to show you what 2x equals 2y has in common with x equals y. Let's take a look. So welcome into Desmos, everybody. Now let's take a look here. We're just going to start right off the bat and just say 2x equals 2y. Now, 2x equals 2y isn't something you're going to run into very often because normally the system you're going to want to have just y, right? You're not going to want to have 2y. You're going to want to have just y. So we've got 2x equals 2y. Now, what happens if I plug x equals y in? Well, notice they're the exact same line, right? If you go to solve and reduce 2y to just y, you divide both sides of this equation by 2, and 2x equals 2y becomes x equals y. So you've got here equivalent equations, and it's very obvious because those two lines sit right on top of each other. If I turn off the black line and turn off on the purple one, look, there it is. If I turn back on the black line, there it is. They sit on top of each other, and so as a result, you end up with equivalent equations. Okay? Now, what happens if they're not equivalent? Right, so you see how those equations are the same, right? It's exactly the same. If you divide 2x equals 2y by 2, you get x equals y. And as a result, those lines are exactly alike. It's still just a 45-degree angle up and to the right. No big deal. Exactly the same. So what happens then? What situation would create an inequivalent equation? Well, let's take a look here. We're going to start with x squared minus 1 equals 3. And by the time we're done, we're going to have an equation that is not exactly the same, but still has the same solutions. Let's take a look. So we can really compare this to a very simple example, okay? And let's go ahead and plug it in right now. X squared equals 4. And what happens here is it puts two parallel lines there. That indicates the 2 points at which x squared equals 4. So what I'm going to do is I'm going to put x squared, but then I'm going to put a second one that says y equals 4. Okay? And notice these 2 points where these graphs cross, right here and right here, right? Notice negative 2 and positive 2. Those x coordinates result in that negative 4. But this wasn't the start of our equation. Our equation actually started like this. I'm going to turn these off now. Our equation to begin was actually x squared minus 1. Okay? And our y wasn't 4. It was not 34 either. It was 3. Okay? Now, look at what happens. Let's highlight these points once again. Negative 2 and positive 2, right? So let's turn off our y equals and just look at these two parabolae for a second, right? they're not identical to each other. They don't ever sit on top of each other. In fact, if we were to continue following these parabolae to infinity, they would actually never cross each other. However, when we take into account y equals 4, where it crosses x squared, and y equals 3, where it crosses x squared minus 1, check this out. Look at this. I'm going to highlight blue here, and look at the blue. 2 and negative 2. Highlighting purple. 2 and negative 2. Okay? So while these equations are not equivalent, they're not the same as each other because they result in different graphs. They do, however, have the same solutions. When we set x to squared equal to 4, notice these two lines right here. These two lines are the 2 points at which x squared equals 4. It's when x equals 2 and x equals negative 2. Now, if I set this equal to 3, check this out. Boom. Once again, same as we've had in other instances, these two lines sit right on top of each other, right? Red, green. And I realize some of you are colorblind and probably can't see that I'm even making any change here. But those lines are sitting right on top of each other. And so we can clearly see that while these two equations are definitely not equivalent, right? X squared equals 4 is not the same as x squared minus 1 equals 3. And we can tell that whenever we look at the graph without this equivalency in it, right? But what we do know is that they have the same solutions. And that's the important part here. Okay, so now we're getting it. Now we're seeing that even though x squared minus 1 equals 3 isn't equivalent, it doesn't have the same graph as x squared equals 4, they have the same solutions. And so while they're inequivalent in a way, since they have the same solution, we can use one to help solve the other. Or by turning one into the other, right, we can help it solve. That's the point of this, right, is being able to isolate certain features of a function and then solve based on that. Let's take a look at a couple more examples where we're going to create inequivalent equations. And what we're going to do is we're going to look at both the graph and the algebra so we can see that, okay, these aren't exactly alike, but they're going to end up turning in our favor. Okay, so let's talk about these inequivalent equations then and see what we've got going on here. So we're going to start with x plus 3 divided by 2 equals 4. Now, right off the bat, the first thing I notice is this fraction right here, okay? And what we want to do in this situation is we always want to get rid of this fraction, okay? Because what this tells us is that half of x plus 3 is equal to 4. So if we can figure out what divided by 2 equals 4, then we know what x plus 3 must be equal to. And so what we're going to do is we're going to multiply both sides of this equation by 2. And in doing so, we'll neutralize that, and we'll find out what divided by 2 equals 4. Now, of course, we're intelligent people, and we know that 8 is what gets halved to make 4. So 8 equals x plus 3, right? From there, we subtract 3 from both sides of the equation, and we get x equals 5. Okay, so in this case, right, x equals 5. Let's look at a second option, though. Let's look at a second equation. And that second equation I want to look at is almost the same. We're going to use some similar numbers here. X plus 3 squared equals 4. Okay, so once again, right, what I know is that whenever I get to this step here, after I resolve this, whatever this result is, if I square it, it's going to equal 4. So my question then becomes, what's the square root of 4? What squares to make 4? So in this case, what we're going to do is we're going to take this square root of both sides. And when we do it on the right side, something interesting has to happen. First, let's resolve the left side, right? This square root cancels out this square symbol and leaves us with x plus 3. And this is going to equal something, okay? Now, we're going to put our square root of 4 symbol here, but because we were neutralizing this square right here, we must account for both the positive and negative roots. So we're actually going to use that plus minus symbol right here, okay? So what this means is that this actually needs to split into two equations. So let's go ahead and do that now. You get x plus 3 equals positive 2, and x plus 3 equals negative 2, right? We split this now into two separate equations. Subtract 3 from both sides of the equation in both equations. That gives you x equals negative 5 in the negative equation, and x equals negative 1 in the positive equation. Okay? And so as you see here, we've actually got two situations where those inequivalent equations that aren't exactly alike produce identical solutions, identical results that we can plug into either of those two equations, and it still provides us with a solution, a true statement, and a full equation in this instance. So I hope that made a little bit more sense now. I hope to see you next time in class. If you do have any questions, don't hesitate to use the comment section down below, the parking lot in our class on Schoology, or even visit the Discord channel where we can go ahead and take a look in the study hall, okay? Until then, have a wonderful rest of your day. I'll see you in class.